we know that a DC generator uses electromagnetic induction to convert mechanical energy into electrical energy. It is frequently used in houses and offices. But do you know how it is constructed? Let's try to understand this. A DC generator consists of a magnetic frame or yoke, the pole core, the pole coils or field coils, the armature core, the armature windings, the commutator, the brushes, and the bearings. Out of these parts, the pole core, the armature core, the yoke, and air gaps between the poles and the armature core form the magnetic circuit. Let's briefly describe each of these components. Yoke is the outer frame of a DC generator which serves two purposes. It acts as a protecting shield for the generator and provides mechanical support for the poles. In small generators, where cheapness rather than weight is the main consideration, yokes are made of cast iron. But for large generators, yokes are usually made of cast steel or rolled steel. Field magnet consists of the pole core and the pole shoes. It basically spreads out the flux in the air gap. Since it generally has a large cross-section, so it reduces reluctance of the magnetic path. It acts as a support for the field coils. Pole coils consist of the copper wire or strip which is wounded on the former. After getting the correct dimensions, the former is removed and the wound coil is put into place over the core. When current is passed through these coils, the poles get electromagnetized and produce the necessary flux that is cut by revolving the armature conductors. Armature core houses the armature conductors or coils and causes them to rotate, cutting the magnetic flux of the field magnet. It also provides a path of very low reluctance to the flux through the armature. It is cylindrical or drum-shaped and is built up of usually circular sheet steel discs or laminations approximately 0.5 mm thick. The slots are either die-cut or punched on the outer periphery of the disc, and the keyway is located in the inner diameter. Armature windings are mostly employed for the armature of a DC machine. They are of two types: lap windings and wave windings. The difference between the two is merely due to the different arrangement of connections at the front or commutator end of the armature. In lap winding, the number of parallel paths is always equal to the number of poles and also the number of brushes. It is suitable for high current, low voltage machines like welding plants. Whereas in wave winding, the number of parallel paths is always 2, and there may be 2 or more brush positions. It is suitable for high voltage, low current machines like generators used for lighting. Commutator facilitates the collection of current from the armature conductors and converts the alternating current induced in the armature conductors into unidirectional current in the external load circuit. It is of cylindrical structure and is built up of wedge-shaped segments of high conductivity, hard-drawn or drop-forged copper. The segments are insulated from each other by thin layers of mica, and the number of segments is equal to the number of armature coils. Brushes collect current from the commutator. They are usually made of carbon or graphite and are in the shape of a rectangular block. They are housed in the brush holder, which is mounted on the spindle. These brushes can slide in the rectangular box, which is open at both the ends. A flexible copper pigtail mounted at the top of the brush conveys current from the brushes to the holder. The number of brushes per spindle depends upon the magnitude of the current to be collected from the commutator. And ball bearings are frequently employed because of their reliability. The ball and rollers are generally packed in hard oil for quieter operations. Note that sleeve bearings are used in order to reduce bearing wear. Basically, the schematic diagram of a DC generator is as shown, and its main parts are: explain